Hello, welcome back, class. So we're gonna start a new topic. It's a very exciting new topic about computational graph and the very basic neural network knowledge. Okay, so the concepts of neural network of computational graph first is a technique that we will basically use, or at least mentioned throughout the whole class, throughout the whole course. And it is one of the most key technical concepts applied in most of the current machine learning frameworks, like you name it, the PyTorch or TensorFlows or whatever frameworks that are based on basically any kind of programming languages. Such a graph is always a concept that will basically everything implemented or designed for machine learning tasks are based on. Okay, so we will use simple examples to introduce computation graph, and then we will basically extend it to the problem of logistic regression that we are familiar with. And in particular, we're gonna focus on the vectorized version of logistic regression, which is that we don't deal with simple data instances or data examples, but we are dealing with like vectorized batch of data. Okay, and lastly, I hope I can also cover the basic one hidden layer neural network for today. All right. Okay, so first of all, what is a computation graph? It's actually just a fancy name to describe some tool that most of the that's the current state-of-the-art machine learning frameworks use to design and to visualize machine learning models. Okay, so actually we will start with a very simple arithmetic example. Right, so machine learning models need to use cost function as some objective function to optimize, to minimize the cost function. So let's say our cost function here, J of ABC, and the A and B and C are the inputs we have. Okay, they can be any part of the data, like any transformation of the data, but we don't care about the details, but we just assume that there are three inputs. Okay, and it's a very simple combination of these three input variables, which is 2 times A times B plus C. Okay, so this is how our cost function is defined, or let's say it's our target function. Okay, so actually how we represent this target function in a machine learning frameworks or in the language of machine learning models, we basically want to be clear about how each step of the computation is defined. Okay, so because it's not a one-time computation, there is a multiplication between A and B, and the summation between the result of A times B plus C. And then the summation results will be timed with some constant too. So it's actually a multiple step computation. So in order to clearly illustrate the computation steps, we will need to use some intermediate variables. Okay, so in this case, we will need to use the variable U for the results of A times B, and the variable V for the results of U plus C, in which U is A times B. Okay, we will use these two intermediate variables. All right, so given these intermediate variables, we can plot the graphs by basically we put the inputs on the left side. So for the first variable U, A and B would be the inputs, and U is the result of taking A and B as the inputs and multiply them together. So we will write U equals A times B on the right within a box. So that is our intermediate output for U. All right, and the output for this box, right, is U, and U will be added with C. Okay, so this second box is the computation for the second intermediate variable V. Okay. Sorry about that. Okay, so now we have U and V defined, right? And the last step is to use a constant 2 times the results of V. All right. So now we have boxes and the arrows connecting those boxes. So basically, we can think of a box as a computation step. Okay, the box here is represents the step or the computation of A multiplies B. The incoming arrows indicates the input. The outcoming arrows indicate the output variable, which is U. Okay, so U will be the output for the first box, while it is also the input for the second box. The second box is the computation for this summation step, and the last box is for the multiplication step. All right. So in this way, we decompose the computation, even though it's a very simple one, into several steps with intermediate variables represented. All right. So now let's take some concrete values like 3 to 5. No, there's no specific reason for the 2. It's just a random number. Yeah, it can be any number that you wish to have. So if we take the concrete inputs values for A equals 3, B equals 2, then we can directly compute the values for U, which is 3 times 2, right? Which is 6. And the V will be 6 plus 5 because the value for C is 5 and the value for U, which we just computed, is 6. And that is 11. And the J would be 2 times 11 would be 22. Yeah. Yeah, I see a comment that it is a magnified look at what those neural network visualizations look like. So that is basically true for a neural network computation, which is certainly more complex than these simple expressions. The internal structures, if you visualize a model in, for example, in TensorFlow, they have a tool called TensorBoard that visualize how the input connects to output. Then you will see a lot of those arrows and boxes connected in that visualized results. Yeah, I would say it's a pretty similar mechanism here. All right, so now given this computation graph plotted and the intermediate results also written besides each box, we're able to look at the question or to examine the question of how the input change will lead to the output change. That is basically one of the most critical questions that we are actually interested in about a model. Okay, well, we will want a model to describe how the input end would affect output end. Okay, so let's see through this computation graph how the slight change in the inputs will lead to the output, or leads to the change of output. So now what we already know here is that the input values is 3, 2, and 5, and the output value is 22. Okay, so now we're looking at how a slight change in one of those input variables, A or B and C, will lead to the change in the J. Okay, for example, how much will J change if A changes a little bit? Okay, what about we now have a slight increase in A from 3 to 3.1, right? So we can do this step by step by computing the new U, which is 3.1 now 3.1 times 2, which is 6.2. And the next node 6.2 plus 5 is 11.2. And the final result would be 22.4, right? Which is different, of course, different from this old value. Okay, so the J also changed. So now, given these variables, we're able to compute how much change in A would lead to, how much change the J will result in given the little change in A, right? So this is a very clear one-on-one mapping relationship. Okay, all right. So this kind of relates to the derivative idea, right? In calculus, we want to see how the value of function's value change when the input changes a little bit. All right. So that is actually we are actually describing the derivatives of the cost function J with respect to A, right? So now let's say the partial derivative of the cost function with respect to A is actually can be defined by the relative change of J over the relative change of A, right? Although we basically need to make sure that the change in A is very little, right? In the mathematical languages, we need to have the limit value when the delta of A, which is the change value of delta of A, is a really a small value. Okay, but in this example, we just want to showcase the relationship. So we will use it's rather a coarse approximation here. All right, so that'll give us 4. So we can say that, let's just claim that the J will change by 4 units if A changes by 1, right? This ratio, this partial derivative of J of A equals 4. So this quantity 4, which basically has such a meaning, right? If we change A by 1 unit, then the output will change by 4 units. Okay. Alrighty. So no, in this case, yeah, in this case, 0.0 is the smallest unit, right? But of course, if we say the A is changed by 0.01, that could also be a 1 unit, right? This is a very flexible. So now we are going to look at some more advanced question. Like, given that the whole graph is plotted, what about now let's go backward, okay? Because all the previous steps we did are basically from the input to the output, okay? Like we given the input value, we compute the intermediates values u and v to u, u to v, v to j, right? So now, because it's the partial derivatives of the cost function with respect to some inputs, we can actually utilize the principle that we already used when we derived the the gradients for logistic regression, right? When we derive the gradients for the cost functions, we use some principle called the chain rule of derivatives. So now we are basically considering these chain rules, but we don't call it chain rules here as for now. We will just look at how much change in the intermediate variables will lead to the change of the cost function, of the output function, right? So let's now focus on the connection from the V, which is the intermediate variable, to the J, which is the output, okay? So we just look at how much V has changed, which is 11.2 from the old value 11. Remember on the previous slide, the old value for V is 11. And so the derivatives of J with respect to V is the change of J over the change of V, which is 2, right? And let's go one more step further back. if we look at the connection between the V to U, right, then we can do the same calculation. The relative change of V with respect to the relative change of U, okay? Or let's say the partial derivative of V with respect to U is the ratio of the change in V over the change of U, right? Which is 0.2 over 0.2, which is 1. Okay, now we have these two quantities. And now let's go back one more step regarding this computation step, okay, from A to U. So the change of U over the change of A is 2, right? Because we use the current value 6.2 minus the old value of 6. All right, we have these 2, 1, and 2 as partial derivatives computed. What we can do is to use, now let's actually use the chain rule, okay? Because according to the principles in calculus, we can multiply these three quantities, right? Which is the partial derivative of, so this one is here, right? The one in the middle is here. The one on the left is here, right? If we multiply these three items together, you can see we can basically like eliminate those variables, quantities here. Okay, so the remaining part is the partial derivative of J with respect to A. Okay, and the result is 2 times 1 times 2. Okay, which is exactly the result of the direct computation. Okay, so this is a proof of concept to show that given a complete computation graph, we can actually compute the partial derivatives between the adjacent variables, right? We compute the adjacent variables and multiply them together, use the chain rules, so that we can gain the knowledge of the partial derivatives of the output with respect to some inputs that are very far away from it, right? A is very far away from the output J here. But since now we can compute the partial derivatives with this step to this step, right? Second step, third step. Now multiplying them together will give us the results that we want, okay? So I think you may ask that why we want to do this, because we can, by simply change little value in A and then observe the output to see how that changes, right? It's the difference between these two approaches is not, I would say, not that such a big difference. But as we have used more complex expressions to define the computation graph, we are able, we're basically facing a problems. If we want to change a little bit in A and get some output, that'll be too much computation going on. Okay, but if we are able to figure out the relationship between these components, right, we can, as long as we know those partial derivatives already, then we can simply use these partial derivatives to multiply together without doing the computation over and over again. Use the outputs with respect to the inputs. Okay. So yeah, so this is an example. I would say a very simple example to show what we can do given the computation graph. Okay. So next, we're gonna extend this a bit to all the inputs, not just to A. Okay. So we're doing this like in a really incremental style. Right, we just, let's do the same thing to B and C, right? With respect to B, if we follow the red flows here from J to V and then V to U and U to V, we would have such an product 2.1, 2 times 1 times 3, which is 6. All right. If we use that long arrow to compute C, then we would have this result, 2.1, right? 2 multiply 2 or multiply 1. If we now let's introduce a new concept called forward step or forward pass. So in a forward pass, what we basically do is to compute the cost function, and the backward pass, which is indicated by the red arrows, we are able to compute the derivatives of the cost function with respect to some variables of our interest. Right. So on this graph, the backward is not complete because I didn't draw the arrow here from U to A, and this is in the previous slide. I think we already plot that. Yes. Okay. So it shows a paradigm that given a computation graph, we can do the forward computation and then use the backward computation to compute the derivatives of the output with respect to the inputs. Okay. All right. So now let's zoom in a little bit just to consider the principles or the rules that connects two nodes or connects adjacent nodes to adjacent nodes. Okay, so let's say we have two nodes and the input is Ni, the output is Ni plus 1, and there could be more nodes like between Ni plus 1 to the final output, right? But we just don't care about all the nodes that is after Ni plus 1. And also we don't care about whether there are more nodes before Ni. So we're just studying the relationships between these two nodes, Ni and I plus 1 here. And we assume that we have the knowledge. We know that it is a certain type of function. F function is connecting Ni to Ni plus 1. All right. So now given the outputs, we also assume that the output is known. And also the partial derivatives of the outputs with respect to Ni plus 1 is also known. Then given this information, we are able to compute the partial derivatives of L with respect to Ni with Ni, which is the node before Ni plus 1. Okay, so now the question is, given this one, how do we compute this one? Okay, so it's actually based on the example that we shown previously. We can simply use the chain rules. Okay, we can use the partial derivative of the outputs with respect to Ni plus 1, which is known, right, times the partial derivatives of Ni plus 1 with respect to Ni. Okay, so this quantity here is actually defined by the F here. Okay, the F is known, so we can know the derivatives of F. So this F prime is for the derivative of F, and we want to know the derivative of this function at the point of Ni, and this is the partial derivative. This is exactly the partial derivative defined in here. Okay, which is the F prime of Ni. Okay, so we can actually compute the partial derivative of the outputs with respect to Ni by using the node that is after the Ni. Okay. Okay, so now let's give this quantity a shorthand or a shortcut. Let's say a short name. Okay, so this partial derivative of the loss with respect to Ni plus 1 is just too long to write. Okay, and we know that this is some quantity, and we can call it a gradients. Okay, it's the gradients of the loss with respect to Ni plus 1. But it's too long to write, so we can use a shorter name, which is d of ni plus 1. Okay, so this d indicates a very small value, indicates it's a gradient. Okay, so now we using this short notation, we are able to like rewrite this formula here as f prime of ni times d of ni plus 1. Okay, and now of course we can rewrite this quantity, use the same notation, d of ni. Okay, so that the whole take-home message from this slide is that when we want to know the derivative of one node, we can simply look at the adjacent node. Okay, and it can be actually referred from the derivative of the adjacent node and the function that connects them. Okay, in order to know dni, in order to know this one, we just need to know this one, the one before the ni. All right. So if you want to ask how do we get this one, then we simply go one more step. We need to know this one, dni minus 1, right? Until we get exactly the immediate connection from the output, right? So this is exactly how the chain rules applied to the computation graph. All right. All right. So actually, this is a practice page on the slide, and given this two different types of functions, right? So everything on the left and the right, they are actually the same except for the f functions. The left f function is a sigmoid function that we are familiar with. Okay, so this function is a 10H function that is also commonly used as an activation function in neural network. Okay, but everything else is the same. We simply need to compute the derivatives of the f, right, given this function, and the value at ni, and times di plus 1 as the value for dni. All right, so I'm going to show the answer right now. So if you work it on paper, you will find that if the function is a sigmoid function, then taking the derivatives of the function itself would result in the function itself times 1 minus the function of itself. Okay, it's basically this form times d of ni plus 1, right? Which is, again, this value. Okay. So because we use, because the value ni plus 1 is a function applied to ni, so we can basically substitute this into the f of n here, which will give us ni plus 1 times 1 minus ni plus 1 times d of ni plus 1. All right, so that's it for the left parts. And the right actually is the similar task that you can do on your paper. So the derivative of this 10H function can actually is also 1 minus the square of the function value itself. Okay, the function value is f of ni, which is ni plus 1. Okay. All right. So hopefully these practices and all the slides before have laid out the concept for computation graphs. And this concept of computation graphs will be a useful way of visualized thinking about how complex machine learning models can be understood, can be visually understood. Okay. So now let's take a further step to logistic regressions. Okay. Now we have very complex functions, right? Relatively speaking, at least if you compare it with the simple linear expressions. Well, not linear, but the simple mathematical expressions on the previous in the previous example. So now let's review the equations for logistic regression a little bit. We need to first use this linear combination, W transpose times X plus B, as the intermediate result, Z, right? this z will be fed into the sigmoid function and to compute the y hat, which is the probability that y belongs to class 1, right? And these again, now let's give an alternative name called A. So A and y hat is actually the same thing, but let's give it a name because A is for activation, which is a term that we use for neural net. Okay, so this activation, this variable is again fed as the input into the next block, right? The next step is that we use the ground truth y times logarithm of A plus 1 minus y times logarithm of 1 minus A. Okay, that is a logistic regression results. Okay, so we have 3 steps of computation, which means we can plot the computation graph rather easily. Okay, and here the L is for the loss. Okay, so loss is I would say a kind of a cost defined on a single training example. Okay, because when we define cost function, we need to have the sigma summation, right, applied to all the training examples. But now since we only care about this one example, we are just using the loss function. Okay, all right. So having these equations written down, we are able to draw the computation graphs quite easily, okay? Because now we have inputs is our x, and we assume that this is a 2-dimensional input examples. X is a vector of 2 dimensions. We have x1, x2, so w will also be 2-dimensional, which is w1, w2, and the b is the intercept parameter here. So the first step is to z, and we put z in this box, and the second step A as this second box, and the last step is to compute the L. Okay. All right. That is the analogy from the simple computation graph to the graph for computation or for logistic regression. And similarly, we can not only do the forward computation, but also we can use the backward arrow to compute the partial derivatives of the loss with respect to each inputs, with respect to each intermediate variable. Okay, so in this particular case, we are interested in the partial derivatives of the loss with respect to A, right? Because A is our intermediate variable. So now we know the loss is in this form. If we take a derivative of this loss function with respect to A, then all the logarithms will be gone, right? And the logarithm will be the denominator's terms here, right? So that is a form for the partial derivative of L with respect to A. Now let's also use the short name, right? Let's call it dA, and the dA is for the derivative with respect to A, but dA is much shorter form than this than using this formula. Okay. All right. So now the arrow goes one more step back, which means we're able to compute the partial derivatives with respect to z now. Okay. So it's time to apply some chain rules, right? Because we want to know this one, the partial derivative with respect to z, and we know that this can decompose into 2 steps. Okay, the step on the left, this one is already known, right? And the second component is here. And this partial derivative of A with respect to z, this is the partial derivative or the derivative of this sigmoid function. And we know that the sigmoid function in the practice 2 slides ago, we already did that, right? It's 1 minus A times A. Okay, so we can use dA times 1 minus A times A to indicate that this is the partial derivative with respect to z, and the short name for it is z. Okay, and if we substitute this very complex term into here, and we find that it eliminates with this items. So a minus 1 will be the value for the dz computed here. Yeah, we call the dz as a shortening. Okay, yeah, we are reaching there. The goal is to go from the outputs right back to the inputs, right? We want to know the derivatives of the L with respect to W's, right? With respect to the W's here, W's and the B's here. Now let's look at all the arrows go backward this way, okay? If it's W1, right, we use the chain rule. The derivative of dz times the derivative of z with respect to W1, okay? So this is quite easy, right? Because it's a linear function, right? The derivative of z with respect to W1 is simply the coefficient x1 here, okay? So we have a minus y times x1 here. And for that's dW1. And for dW2, we will have the same results, right? We'll have the same results. And for dB, since the coefficient is 1 here, so the results will be a minus 1. All right, we have all the results computed, and we are very happy about that, okay? Because now we know the gradients with respect to all the parameters, right? With all the parameters. Okay, so you know what? This is actually quite, this is something that you should be very familiar with, because when we first introduced logarithm, we first introduced logistic regression, we derived the cost function, right, as the summation of these whole bunch of laws, and we directly take derivative of L, okay, with respect this complex term with respect to W1, W2, right, and B. And actually we had a similar results as this one, okay? But now since on this page is not the cost function, but the loss function, it's just the loss defined to each data example. So all the gradients are in more simpler forms. All right. Say we look at more examples rather than one data example, okay? And of course, we know the cost function will be the summation of the loss defined on each instance. Okay, so I think here it shouldn't be a subtraction. Okay, it should be just a comma. Okay, yeah, it shouldn't be a subtraction. So, but now we need to sum up all the data examples and normalize by m, which is for the convenience of computation. Okay, so we can see that if we implement it like this, we can implement it as a way to basically we move the partial derivatives with respect to W inside the summation, right? So it's basically the average results of all the gradients for each data points. Okay. All right. So now let's look at how do we implement that when we compute the gradients for m examples. Okay. So we can implement it with a for loop. And remember, our goal is here, right? The gradients with respect to W1 should be here. It's the average results for each data instance, for data example. So here we need to, first line of code is to initialize all the gradients to 0 for all the W's, assuming that we have n dimensions. And also the B is also initialized to 0, okay? And then we use this for loop, okay? Because we need to iterate over all data examples to first compute the forward pass, okay? That is the forward pass, okay? We first compute Zi, okay? Zi, that is just the first step of the computation graph, right? Zi and the AI and the DZ, right? DZ is AI minus YI, right? Okay, so this is, let me be more specific. These two are the forward examples, forward pass. Okay, because according to the previous slide, we know that the dA, the dz is actually a minus 1, right? So we can directly apply this principle that the dzi is ai minus yi. Okay, so now we need to accumulate the values for dw, right? Now we have a subscript, subscript j equals from 1 to n, because we have n dimensions for the parameters. Okay, so for each for each dimensions, the dwj will be accumulated to this xj times dz. So this is also the principle from the previous slide. Okay, and the dw will also be accumulated by each dzi. All right, and after the whole for loop is done, okay, after this whole loop is done, forward and backward step is done, we should compute the average values for dw1 to dwn and also db. Okay, and after the left part is done, the part in the gradients in the dashed line box is done. We have computed the gradients for w's and b's, and then on the right we can use gradient descent to update the parameters using the formula here. Okay, but since there are a lot of for loops, and we basically want to vectorize, for example, particularly this step, right? The inside the for loop, it is a loop over n dimensionalities, which is definitely can be vectorized in Python, right? If we want to, it's okay if we write a pseudocode like this when we introduce some ideas, but for for implementation, we should always vectorize the computation. So let's see what we can do here. It's basically, I guess you are already more or less familiar with this concept, because everything you have implemented for logistic regression and for linear regression, when you compute the dot product between two vectors, it's already a vectorized operation. Okay, but now let's see this more particular example of vectorized code. Here, if we want to compute the dot products, we basically don't use the for loop, but we use the dot product. Okay, and I will skip this real quick, because in Python we already know that if we use the vectorized version, we will have a much more quick response, quick computation speed. Okay, so now let's see how we can vectorize the forward pass for the logistic regression. Okay, because all the data are same dimensions, we can basically place each data example into one column vector, and the whole data training data would be a n by n matrices. Okay, so if we look at, think of it, the data from a matrix perspective, right? It's an n by n. Then we can basically use the double transpose times this capital X. Okay, and the double transpose is a long row vectors from W1 to W2, blah, 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 until Wn, right? So if you use this long row vector times this X, we will have such a results. Okay, so the dimensions of W transpose must match with X. Okay, because when we do the matrix multiplication or vector multiplication, we need to make sure that the dimensions match. Otherwise, it won't work. Okay, so in this case, actually this step we can actually also use the capital Z to indicate the results, which is a n dimensional vectors, right? Which we have n components from Z1 to Z2 to Zn. And this whole line of computation can actually be achieved by this one line numpy command. Okay, so this final B will be automatically broadcasted to all the vectors resulting from here. Okay, so for the activations, it's also vectorizable because the activations A1 is the sigmoid of Z1, A2 is a sigmoid of Z2. So we can simply by apply these activation function to Z. I think you have already done this in logistic regression, right? So yeah, let's go through this quickly. All right. So now the tricky part is a little bit trickier part is the vectorization for the backward style. Not style, but for the backward pass. Okay, because in the backward pass we need to compute the DZ1, DZ2, and the DZM, right? We need to basically vectorize them into such a form, right? It's actually quite easy for DZ. It's just capital A minus Y, which will automatically give you such many subtractions, such many differences. Okay, so now let's look at the whole computation process again. I crossed out these steps because they are all vectorized. Okay, and the dB is simply the summation of all all DZs. Right, it's also doable in vectorizable in NumPy. So the remaining parts is DW. Okay, so we need to figure out a way to vectorize the DW. Okay, actually DW can be computed in this way. DW is 1/n times x times dz transposed. Okay, so what is dz? Let's look at the shape of dz. dz, according to our previous slide, let me find it. dz, right? dz in such a shape, right? dz is a one row vector that has m columns. It has m elements, right? dz is like this. What about if we transpose dz? Then it will be a column vector, right? It has m rows, and the result of multiplying the x that has n rows and m columns, right? M is the number of columns, with a m row column vector would result in something that is n columns and n rows and with one column, right? So say each column in here, actually each row in here corresponding to the same feature with the same x with the same subscript 1 here. Yeah, that's the data for the first dimension. Okay, so that corresponds to the gradients for dw1 for the first dimension. Okay, and the second is for the dw2, which is correspond to this column, this row. Okay. Okay, so the I think I should write for this one. I think I should write either D capital W or switch the capital X with lowercase x. Yeah, I will figure out that out later and fix the slide later. Okay, but anyway, if I put the capital X here and the dz as a column vector here, the result would be a column vector of for dw. Okay, so we basically also cross out this step. Basically, we don't need to use a for loop to compute the dw. Okay, so now we are pretty much done. But there's still a for loop out there, right? There's a for loop from 1 to m, and this step is actually not that easy to vectorize because basically we iterate over all m examples, right? And we don't know the number of m's at the beginning. So unless we are doing some mini batch optimization, we know the batch size for each iteration. We are able to consider a batch data as a fixed sized tensor. Then we are able to apply vectorized operation on it. But otherwise, we were not going to vectorize the most outer for loop. Okay, so now let's put everything together. If we have x data and the wb all vectorized, okay, so the x is a matrix now. So z would be x transpose times x plus b. Now z is also in capitalized version, and a is also capitalized. A is also a matrix, and the j would be the results of summation of all the loss. Okay, and in the backward style, in the backward pass, the gradients for z, which is dz, is the difference between a minus y, and the dw is the results of x times dz transpose. Okay, dz is a row vector, so dz transpose would be a column vector. That is for dw, and db is the summation of dz's divided by m. Okay. And now after the computation is done, we are able to use gradient descent to update the parameters. Okay, so within each step of gradient descent, we have the for loops. That is the two for loops. That is the two forward steps, and all these parts are the backward steps. Okay, and these two are the parameter updating steps. So this is basically how the vectorized logistic regression represented by some computation graphs and the whole process described by the computation graph, how it looks like. Yeah. So we have a pretty dense representation for logistic regression. It's a lot of equations, but it's actually, in mathematical principles, it's actually a pretty simple process. So we can wrap everything into a single unit to represent a logistic regression. Okay, so we can simply combine the linear part with the activation part into one unit, and the result is a much more compact example and a much compact representation of the graph. Okay, we simply put a circle here and divide it into two halves. On the left half is a computation for z. On the right half is computation for a. So we know that z is the linear combination of between w and x plus b, and a is the sigmoid applied to z. Okay, so that is the basic unit for the logistic regression, and that also forms the basic unit that we will use to build neural network models. Okay, so now let's quickly enter the neural network. All right, so before that, any questions that you would like to ask right now? All right, good. So let's look at the neural network. All right, so actually we can think of neural network a stack of basic neurons. Okay, a stack of basic logistic regression units. Okay, so now if you look at the top units here, we have Z1, which is with the superscript in brackets 1. Okay, so if we look at Z1, Z1 is actually computed with the parameter W1 with also 1 in the superscript transposed times x plus B1. Okay, and the B1 is also has this superscript. Okay, so A1 is the results of applying the sigma function to Z1, right? And similarly, we can do Z2, and Z2 is the results of applying a linear combination with a different set of parameters. So the W2 is in yellow color. They are different parameters, okay, because each unit has its own parameters. So the Z2 is its own parameters times X plus B2. And A2 is the result of applying sigmoid to Z2. And Z31 is the result of applying the green parameters W3 to X. And A3 is the sigmoid applied to Z3. All right, now Z2, we have a different parameter. So for Z2, because it's at a different layer, okay, we call this is the first layer. So that's why all the parameters has the ones indicated, right? Has the ones associated to each parameter and the ones associated to each activations. So the Z2 is actually the second layer, okay? So it's actually a different layer with the first layer. Then Z2 is W2 transposed, and the W2 is the parameter associated to the left half of the model, okay? And A2 is the sigmoid of Z2. So that's pretty much a neural network, right? So it's actually not that complex to understand, because once we know a complete graph for logistic regressions, we're able to simply build a very complex models, taking all the neurons by putting all the neurons together.
Professor?
Yes.
So in the Z with the subscript 2, the A with the subscript 1, would that be the I guess the matrix or the vector of all values of A's in the first layer?
Yes. So A would be something like A1, 1, A2, 1. Yeah, all A's from the previous layer. I think you are correct.
Okay, thank you.
Yeah. Yeah, so all the outputs from the activation output from the previous layer would be the input for the current layer. Yeah. So the A is a vector like that looks like this way. Yeah. All right. So a more formal definition, right? We can call the data as the inputs layer. And if there's a layer in the middle, we call it the hidden layer, okay? And if that's the outputs, which we directly use as to make predictions, we call it the output layer. And for notations, if we use 0 as a superscript, we can also use a superscript 0 to indicate the first layer, which is the data, all right? But we rarely do that because it doesn't make sense. There's no parameters for the input layer. And for the hidden layer, if it's layer 1, then we put the 1 in the superscript. If it's a layer 2, we use 2 put into the superscript. And now that we have parameters, okay. So now we have this capital letter for B. Okay, so this capital letter for actually capital letter for W. Capital W is a collection of parameters associated with all the neurons, all the units in the current layer. And so is W2, okay? So, so the hidden layer, in this case, it's just a logistic regression, okay? There's no SVM or linear regression happened within the hidden layer. So the hidden layer, so what's done within this neuron is a logistic regression computation. It's two halves, Z on the left and A on the right, okay? And this applies to all the neurons here. Okay, so now we have W's. Let's look at what these capital W's look like. Okay, it's actually a matrix. Okay, and it's a 4-row by 3-column in this particular example. And how do we memorize the shape of a W? Okay, so it's also easy to memorize because if we want, if there are 4 outputs, if there are 4 outputs for the current layer, then it is 4 rows. And if there are 3 inputs in the previous layer, then the number of columns is 3. Okay, so the number of columns matches the number of the inputs, and the number of rows is the number of outputs for this current layer. Okay. And now W is a matrix. Since it's a matrix, it also has indices to indicate the entries, right? So the ith row and the jth column is actually the weights that connect the jth unit in the outputs. Actually, the jth unit in the input to the ith unit in the layer L. Okay, so if we try to understand this, right? If we look at the first row, it's the W11 to W12 and W13. So it actually corresponds to the W's that connects X1 to A1 and X2 to A1 and X3 to A1. Okay, it corresponds to the weights that's indicated by the red arrows. Okay, and B1 is also a vector, which we call a bias vector, and each element for B is applied to each output unit here. So actually, there should be a 1 as input here, but nowadays we don't rarely draw that. Yeah. It's basically a default option for a neural network to have those bias inputs. Okay. And if we look at W2, and it's a little bit special because W2 only needs to output, the second layer only needs to output only has one output unit. So the number of rows in W2 is 1, okay? And it takes 4 inputs as 4 inputs. And so the number of columns in W2 is 4. And also for the bias for 2 is just one number, one scalar variable. All right, so given the structure of the network like this, we're able to compute the outputs. Okay, so let's just use one training example as input. Okay, so if we have one training example, which is x, the vector x from x1 to x3, then we can first compute z1, right, and a1. And then we can compute Z1, Z2, and A2, right? But how do we compute all the units all at once? Then we basically need to vectorize it, right? So basically, we should represent the W1s, the W's, the lowercase w's into the uppercase W. Okay, so and also all the x as the inputs as all the x as a column vector here. Okay, so and all the b's will also be laid out as the column vector here, which is the result of applying to a matrix to the result of a matrix multiplication. And then we have z's. Z's is also a 4x1 column vector. And the A is applied to Z, which means A is the same direction, is in the same dimension of Z. Okay, so here it's just a vectorized representation for the computation, for the forward computation. So this box here is something we called W1. Yeah, it's exactly how we define W1 and how we define the B1. Okay, so each row, if you look at the meaning of the first row of W1, it's just the lowercase W1 that tells you how you compute the output for Z1. Okay. All right, vectorized representation. Here's some details that's about the dimensions that you can use to check whether you have correctly understand the connections of neural network. So you basically need to find the dimensions match. Okay, you need to find the matching dimensions here, which is here and here. Okay, the dimensions should always match. So the dimensions for the else layer should match these. The number of columns in WL should be NL-1, which matches the number of rows in the activation from the previous layer. Okay. So these are the typical relationships that you need to find useful in neural network. So let's further see whether we can vectorize the M training examples, because we have a lot of training examples. Because we have such a you can think of it as a one-on-one mapping from the raw inputs X to the final activations A true, right? So we basically want to also vectorize this for loop, right? How do we compute all the outputs like with the vectorized representation? And that's actually similar to what we did for logistic regression, right? We can basically stack all the inputs into columns. Now we have M columns and M rows. We will have an N by M matrix that represents our inputs. And the solution is also just to directly apply the formula for the logistic regression, which is Z1 times W1 times X, and also A1, right? And Z2 will be computed using this A1 as inputs, and A2 will be the outputs. Okay, so now the the X is a matrix, and the Z is also a matrix, and the A's is also matrix. So if you look at the columns of those matrices, they actually match, right? Because when you have M inputs, the intermediates hidden representations, A's and the Z's, they should also have this M columns. Otherwise, the data are lost, right? When you input something into the model, the number of inputs should always match the number of outputs. So these dimensions should always match. And in the outputs, Y is also M columns. All right. So instead of using one training example at a time, we basically need to use M as training M examples at the same time. Okay, that'll basically is the most scientific way to handle a batch of data sets. Okay, so for this programming language Python that we use for this course, we use Python. We use NumPy and also PyTorch in the future, because they all support vectorized computation really well. So you basically need to make sure that whenever it's possible, you need to use vectorized computation. You need to vectorize the implementation rather than use for loops. Yeah, that's pretty much for the neural network representations, and particularly importantly, the vectorized representation for the data, for the parameters, for the intermediates, inputs, outputs, and the final outputs. All right, so last bit of information is why we call such a model, why we call the model with such a structure a neural network. It's basically an analogy to the biological neurons, because we have biological neurons that we have a very long axons that leads to the activations that connects to the another neurons, right? So it's basically an analogical imagination, right? But we didn't actually have solid examples to show that the forward and backward step actually happens in our neural cells. I think these are very advanced topics in neuroscience and the intersection with artificial intelligence. All right, so that's pretty much of it for this chapter. So I would recommend you to go through the slides, especially the ones for the computation graph for logistic regressions. And these will be the basics for our next lecture about the backward propagation algorithms when we talk about multiple layer neural networks. All right. Are there any questions so far? Yeah, I had some pretty good questions during the lecture. Okay, so I have a question about SVM assignments. Okay, so let me stop the recording for now.